Welcome back. In this video, I will go over the principles of centrifugation and how we compare performance of similar types of centrifuge. When solid particles are dispersed in liquid without stabilization, solid particles have the natural tendency to separate from the liquid phase, and that process is driven by gravity, called sedimentation. If we assume that solid particles are spheres, then we can use Stoke's law to describe the flow around the spheres or solid particles at lower velocities. Stoke's law says that the terminal velocity v infinity is equal to the difference of particle and fluid's density divided by 18 times the fluid's viscosity multiplied by the particle's diameter and the driving force of gravitational acceleration. Stoke's law has to satisfy its assumption of low velocity and laminar flow. Usually the assumption is satisfied when the Reynolds number is smaller than 1, where the Reynolds number is defined by the particle diameter multiplied by the terminal velocity times the fluid's density divided by the viscosity of the fluid. However, from our intuition from daily life, sedimentation is very slow, that is, the separation of solid particles dispersed in liquid only by gravitational force is pretty slow. And how can we speed it up? We speed up the separation of the solid particles in the liquid by using centrifugation. Centrifugation uses the driving force of the centrifugal force, and it can also be described by Stoke's law just by replacing the driving force from gravitational force to the angular velocity squared times the centrifuge radius. And the Stoke's law's assumption should also hold so that the Reynolds number is smaller than 1 and the terminal velocity is slow. The picture shown here is a commercial batch centrifuge that are usually used in research labs. We put in the tubes inside the centrifuge bowl and then close the lid, and the centrifuge bowl spin in one direction. The spinning produces a large centrifugal force that pushes the solid content to the bottom of the liquid, and therefore achieving separation of solid particles from the liquid. We can quantify how much larger the centrifugal driving force is compared to the gravitational driving force by using g-force. G-force is the angular velocity of the centrifuge square multiplied by the radius of the centrifuge, which is the centrifugal driving force, normalized by the gravitational driving force, which is the gravitational acceleration. It is the centrifugal divided by the gravitational. Usually the units are xg, which is how much times the gravitational acceleration. Some commercial benchtop centrifuges can achieve up to tens of thousands of xg. Besides batch centrifuge, we can also have continuous centrifuge that are widely used in industry. The types of continuous centrifuge is beyond the scope of this video, but we can look at how we can compare performance of continuous centrifuges of the same type. We can use the sigma factor, or the effective area of the continuous centrifuge, to compare the centrifuges of same type. The sigma factor is defined as the volumetric flow rate divided by 2 times the terminal velocity. And therefore, we have the unit of area for sigma factor. And therefore, it is the effective area of the centrifuge. We can rearrange this equation so we have 2 times the terminal velocity times sigma factor is equal to the flow rate. And if we want to compare 2 centrifuges of the same type, we can have the first centrifuge and label it 1, and then have the second centrifuge and label it 2. And if we take the ratio between them, then we can cancel out the 2. We have that the terminal velocity 1 times sigma factor of 1 divided by the terminal velocity of 2, sigma factor of 2, is equal to the ratio of their volumetric flow rate. Let's look at an example of how we can apply such comparison. So at a small scale, cells can be centrifuged at sigma factor 1 and volumetric flow rate 1. But at a large scale, the parameters change, but it has the same speed. The density and the viscosity are unchanged. We want to quantify the changed physical quantity. We can first write out the equation for comparing using sigma factor. So we have the terminal velocity of 1 times sigma factor of 1 ratio with the 2 is equal to the volumetric flow rates ratio. We already know the volumetric flow rates of the two. We also know the sigma factor of the two, but we don't know the terminal velocity of those two. Remember from the governing equation of Stoke's law for centrifugation, we have that the terminal velocity is equal to the difference between the density particle and the fluid divided by 18 times the viscosity times particle diameter squared times the angular velocity squared times the radius. Because we're taking the ratio, let's write that out. Because we're comparing things, we notice that from the problem, the density does not change. So as it didn't change, the ratio should go to 1. The 18 should also cancel out, and the viscosity did not change, so that also cancels. Because they operate at the same speed, so they should have the same angular velocity, that cancels out. Because they're using the same centrifuge, the radius should also be the same. They cancel out. So this simplifies to the particle diameter of the first one with respect to the second one, multiplied by the sigma factor 1 and 2 is equal to the ratio of the volumetric flow rate. Now we can determine that the changed physical property is the diameter of particle. Now we can quantify how much it has changed. So we can solve for dp1 divided by dp2, which is equal to volumetric flow rates ratio times sigma 2 divided by sigma 1, and taking the square root of that. Now we can plug in the values. So we have 15 with its unit divided by 700 with the same unit. Sigma factor 2 is 9,000 divided by sigma factor 1 is 200 square root. And if we calculate the value for that, we will have 0.98. So that we have the diameter of 1 is equal to 0.98 of the particle diameter 2. We have the small scale particle diameter is smaller than the large scale particle diameter. In this video, I discussed the separation of solid particles from dispersed liquid, first by looking at sedimentation and then centrifugation. Centrifugation is governed by Stoke's law, like sedimentation, and it can be batch or continuous. We can compare the performance of continuous centrifuges of the same type using sigma factors.